Okay, I'm going to start this morning with a little bit. Oh, the clock has been stolen. A little bit of Git. And so this is not at all enough for you to do everything you need to do in Git. Sorry, it's enough for you to do the minimum, but it's not what you should really do as a proper introduction to Git. I have posted in Canvas links to some YouTube videos from other people that show you like a tutorial introduction to Git, how to use Git with Visual Studio, how to use it with Eclipse. So there's a bunch more about tool integration. But based on what we saw for the first programming assignment, I'm not sure people understand what Git is for. I actually thought I gave this lecture, but apparently I gave it in my other class, and I get confused because when you're doing 2 or 3 in a day, it gets mixed up. So I'm going to talk a little bit about Git as a tool for computer science. So first, when you install Git, there's some directories in your home directory, whatever that means, in your operating system. There's a file called .gitconfig. This will have a bunch of information in it about how Git is configured on your machine. And then you'll have a directory called .git, which is in each directory where you use Git. So the first one is in your home directory, the others are whatever directory you install Git, and it contains all the objects, the repository, and a bunch of other stuff. And then there's a way of putting a .gitignore, which will make it ignore some subdirectories. For example, if you're using Visual Studio and you don't want to be checking binaries in, then you can put .gitignore in your .debug and in your release and debug directory, so you can ignore stuff. Again, if you're using a lot of the integrated tools, much of this stuff will be automated. So Git's real advantages. So for a large-scale computer science, Git is extremely resilient. You have repositories in multiple places. Any one of them is sufficient to rebuild all the code from anywhere you want. So no one is the special one, as opposed to something like Visual Source Safe, where there is a particular server that's in charge of everything. If you lose that, you lose everything. So this is a different way of thinking about how to have your stuff distributed. It's extremely fast compared to other things. It's very good at compression, and it's relatively simple once you get through the learning curve to figure out what to do. It has a large user base with robust tools. GitHub was recently acquired by Microsoft, but even before that, Git was extremely large. It's what underlies the Linux distributions, or at least the Linux kernel and the core of almost all of Linux, so that when we're developing core modules, right, it's distributed across all these different developers, and it's designed for that scale of project. Probably overkill for what we need in this class, but I wanted you to get started using it, and you'll see there's some advantages to it. Every semester I have taught this class, I've had 1 or 2 students say, oh, I lost my code, my disk crashed, whatever, right? I will have zero sympathy this semester, because if you're using Git and you're using GitHub, and we've provided so you have those accounts, right, then all of your code should live on a machine that cannot be destroyed by you. No matter how bad things go, right, it'll live someplace else. So Git has a model for storage in terms of doing backups and whatever that is really based on this idea of, so deltas were commonly used in other things. It has what's called a snapshot storage. At any point in time, it looks like you have all your files. You actually have all your files at any model of where you check out. And while there might be some deltas underlying it in its packing technology, this is part of what makes it very fast and easy. If I want to go to one version or another, I just check that version out and you'll be there almost instantaneously. So there's a few basic commands to work with Git. So once you have a Git repo established, which you can actually do by using GitHub, and I will show you in a demo in a second just how to do all of that, using it through the GitHub interface. But once you have it and you've checked it out and cloned it, then the basic commands are to do something like diff. That will show me the difference between the current version of the code and what's been checked in. That's very useful if you're trying to figure out, I changed something and it used to work, now what's not working. You can use that as a sort of difference to any version you want. And a diff will actually allow you to name the version if you want, to look at what you want to change with. You can find out status, what's the difference of all my files. Importantly, I can add a file. So on the command line, I can say git add, in this case, hello.txt. If I were to do git diff now, it would actually show me there's no changes because I've added my file, what's there. I can, as I said, I can do differences in different heads. I can do status again, it'll show me things. So if I were to actually just type all these in on the git bash command line under Windows or the command line in Linux or OS X, you'd see what all these commands do. It's all very simple. You can just go through doing all of that. And then you can commit. If I make some changes, I can add comments when I go to commit stuff. So to understand what Git is really doing and why you want to be using it, it's useful to think of it in terms of the 3 trees of Git. So the first is what's called the head. This is the most recent version in the actual Git repository at GitHub or wherever your Git server happens to be. So that's the head of your Git repo. Now, the head will move over time, but the head is always what is the current version at that place. Then when I start working on it, I'm going to check out the project, and now I will have a working directory with some stuff in it. As I work on that stuff, I will make changes to my local files and whatever that are not reflected or changed in the original repo. At some point, I've staged my files, so I do a git add. That's what's called staging. Now those files are saying, these are files that should go to Git, go to the Git repo. And then when I commit them, they actually get stored as the new head. But this is a little bit tricky because they're stored as the new head locally, not remotely. They don't actually go up to GitHub or wherever your server is until I do a git push. So I can think of it as I can pull them down or I can push them up. But I can do everything locally. And when you're working in your code, I strongly recommend you develop a habit of every time you think you have something worth running to test out an idea, you should commit that because that saves it locally. And the storage implications of committing it is extremely small. If you run it and the experiment doesn't work and you don't like what you did, then you can edit it and commit it again. But I'm sure many of you, although you're younger in your programming career, right, you've probably already experienced making a change you didn't really like and you wanted to go back to that old version of code you had, or at least some snippet of that code. Git, if you keep doing these commits, will give you all of that history so you can go back and say, oh yeah, that was what I did yesterday. That made more sense. I will move on to that. So I'm going to go through very quickly a basic workflow. So assuming I'm doing this on the command line, and then I will show you the web interface after I'm done the slides. So I'm going to start with the command line command git init. This actually creates in the current directory a new Git repo. So you'll notice here on my prompt, I'm in the Git test directory, which I made up in my home directory. And then after I do this, there's a bunch of files in my .git directory. So git init, it actually just creates a first directory. First repository in your current directory. So then I'm going to go through, I'm going to edit my files, I'm going to do whatever. Editing is not built into Git. Git is built into most editors. So if you're using, or has at least interfaces for lots of editors, so Visual Studio, Eclipse, VS Code, Atom, Emacs, Vim, Prime, Notepad++, there's a way of getting Git to work with all of those. And there's a little link here in the slides, which I will post after class, that will take you to instructions on how to install it for a bunch of different editors under Windows. So after I do all this, I'm going to now go ahead and edit my files. So I've done the git init, so I'm going to do a very simple edit here. I'm just going to do echo hello into hello.txt. That just created a file that's got the word hello in it. That's it. If I do git status, now it's going to actually output this information here, which says on branch master. I'll come to the idea of branches in a little bit. And it's got an initial commit. And then it's going to tell me about these untracked files. It's telling me that hello.txt, even though I created it, is not yet tracked. Git knows it exists, but Git's not tracking it. So we want to tell Git to track it. So I'm going to say git add hello.txt. I'm going to do git status. Now it's going to show me I'm the branch master. I'm still in the initial commit. And there's a new file. The new file means it's been added, but it hasn't yet been committed. Now I do the commit. Git commit -am for, I'm going to put the message on the command line. Otherwise, it'll prompt me for one. It's easier to do the demo this way. Demo message. And now it's created the new file. Okay? And I now have a local copy. Even if I never push it to GitHub, I have this local repository of every change I've made every time I do these commits, which is extremely useful for working it as a programmer. So just went through this process, the basic workflow, working directory, git add, put it in the index, git commit, put it in my local version of the repository. So there's a couple things that are useful. I can always view changes if I do git diff. I can show the difference between actually any two named things. I'll show you naming in just a second. I can also do the difference between the stage version, which I have locally, and the head of what I want to do. So if I made something I didn't like, so I can go back to a previous version. So the previous version, I'm now going to check out. Hopefully you guys can read that. I'm going to check out, and I have this number, FF0F. So to understand what that number is, I have to go back a second to this log. When I did the git log, because I didn't name anything, Git names everything by the MD5 hash that's associated with the file. So here it said, here's the name of the commit, FF0F79. There's a long string. Right? I don't have to use the long string. As long as I use a unique identifier or substring that's in the beginning of it, that's good enough. So I'm going to go back to this version of the code, which was the original message. by doing a get checkout minus ff0, and then I'm actually going to call a new branch. And I'll talk about branch. You'll see some graphics for branching in a second. When I do that, I now get a version, and if I actually look at the content of the file, it's back to the old version of the file. And then if I modify it, and then I commit it, so I've now added a line to the file, I can, after I've done that, if I check it back out the original, right, it's going to yell at me in this case, just telling me that I'm in this detached state because I did something, I made a branch, and I never actually did anything with the branch. I just sort of left it hanging out there. And now it's going to, so it's warning me, but that's okay. I can force it to do something new. But after I did that checkout, I can see the new version of the code, or so the old version of the code. Even though I added a line, now I'm back to the original version without that line. And so on. I can check out 03E9, which was this second version, right? And now I look at the file, right? I'm just sort of showing here that you can see each version of your code as you're doing it. So if I've made things I don't like, I can use get checkout to check out a particular version. So when you make those commit messages, that's one of the reasons they're useful, because that's really how you're going to remember which version of your code had what. If I really want to, I can move the tree back to a certain specified version. And if you want to throw away the stuff you've recently been working on, you can say minus force. Okay? This is one of the few times Git will actually throw away stuff. Git is extremely resilient. It's very hard to remove stuff from Git. There's a command called git rm. Even it doesn't remove stuff. It just marks it as removed. If you want to reclaim the storage, you have to do a lot more work to get it back. After I can do a git revert, which reverts back to a particular command. It doesn't actually delete the current the commit object. It just applies a patch to go from one version to another and moves you forward. Okay. Git really never deletes a committed object. It's very hard to shoot yourself in the foot. Even the command, once you've got it in GitHub, even rm minus rf throwaway disk, you can always check it out again later and get them all back. As I said, the git rm command does not do what you think. It will not remove it from the repository. It'll just mark it as removed so that later on when you go to look for stuff, it doesn't show it to you. Unless you say, like, show me everything including the stuff that's deleted, so that it's easier to keep track of stuff. So one of the useful things about Git is its strong ability to do branching and merging. So I'll briefly talk about branching. It's extremely lightweight. It's not a copy as it would be in CVS or Subversion or some of the other source management tools. So in Git, you're actually always on a branch. The only question is what's the name of the branch. Branches can be local branches. They can be remote branches. And the commands that allow you to work with them allow you to do things by viewing branches as sort of like copies of code. Many of you have probably done stuff where you make a copy directory, you put all your stuff here, then you do some work, and then you look at the differences. Or if you haven't, sooner or later, most programmers are doing that kind of stuff. The goal here is to not to actually have separate directories, but to let Git manage all of that for you. So the basic commands are git branch, git merge, and git cherry pick. Branch and merge are pretty obvious. Branch is going to cause us to separate and have two branches. Merge is going to merge two of them together. And cherry pick allows me to take parts of one branch and add them to another, but not take the entire branch. So if I think of the branch as all the files of code I have, maybe I want to choose one or two of those to incorporate into what I do, and that's when I would use cherry pick. So when I go to use branches, I can do git checkout minus b branch, which I just showed you a second ago. I can actually go a little bit deeper. I can say minus b development and then branch, which is the name of the hosting place where we put it, origins, master, some things like that. We'll show those some examples. Okay. If I just do git branch, it lists all the branches that are available. And it'll show me the head of each of those branches, give me a little bit of idea what's going on for them. And then I can, once I'm on a branch, I can do some merging or put stuff together. So let's imagine that here's sort of a tree of stuff. After I start with some base code, I make a commit, then I have underneath the tree all my binary objects and potentially other stuff. And then I can make commits. And as I go to look at this, right now all of this is one branch, right? There's one string of commits. Right, so as I started from my head, I have C1 branching off of C2. And now let's say I want to run some new experiment. I want to try out some idea to see if this works for what I want in my code. So I say git branch experiment. That makes a new branch called experiment, which gives me this blob. And because I didn't say anything else, it's actually, there are two branches, default and experiment. And notice it's got a little star next to the default. That's because while I said make a branch called experiment, I didn't say check out the branch called experiment. I just said to create it. I didn't connect to it. So if I want to connect to it, I actually have to do, say, git checkout experiment, and then my head is now moved to be off the experiment. I can work on this branch. I can do some code. Now I do a git commit, and I've got a new version of my code because the version after my edits is different from what I checked out. I can do another set of edits, do some more commits, and then all of a sudden, if I want to go back to the old version, I just do a git checkout default, and now the head, which is what I'm working on, is over here. I can make some changes here. Do a commit, I get C4. And now I can do git checkout experiment again. I'm back over here and do a commit. So I can keep adding on either branch, trying out ideas and see how see how the ideas expand. Now the problem is now I have these two different branches of what should be ideally the same code. After I figured out what I really want to do, I eventually start cleaning them up by doing merging. So we want to do a merge. There's really two steps to merge. And this is the one place where I see, one of the few places I see students make really serious mistakes, which is if I want to merge, you want to check out the branch you want to merge onto, right? So if I wanted to merge, in this case, the experiment into the default branch, then I want to check out default, not check out experiment, right? So I'm merging into something, on top of something, and I'm going to merge stuff into it. So view it as go where you want to be, and then bring all the other stuff on top of you. Right? Don't go where you want to throw stuff out of. So I do, in this case, git checkout default, and then I do git merge experiment, and it's going to take all of the code from that branch. And if the files are the same, they're transparent. If the files are different, it's going to do what it can for a fast forward merge. It's going to try and merge these two because so far these look like they'll be fast forwards. If I have blocks of code and this file was changed here in one branch and this file was changed here in another branch and there's no overlap in the lines in which they changed, then merge will automatically take the two pieces and put them together. If, however, they overlap on lines, so these lines and these lines actually edited the same lines, then it'll produce what's called a merge conflict and make you do some work to figure out what did you really mean. Now that's both good and bad. It can be dangerous because if I added one definition of the function here, and then in the other edit, I added the same function redefined at the bottom of the file, right? Then they're not going to overlap, but there'll still be a conflict, right? So I'll have to work that out. So it's not magic, but it just basically uses file overlap as a way of deciding when it should or should not deal with all of that. In every operating system and every tool you want to use, there is generally the ability to define what's called a git merge tool, a tool that will actually help you figure out how to do with merging. Most of these show you three windows. So they'll show you the original, so the sort of merged code, the results of merging. It'll show you the first file and the second file, and then you can decide, take the lines that I want from here, from A, or take the lines from B and merge those into the final result. So Visual Studio does that, Eclipse does that. All of them have ways of doing this git merging because it's a very common thing within your programming experience. After I'm done, I can check them out, and then I do a commit. And notice, even after I've done the merge, sorry, I wasn't paying attention. So here I did the merge. So now C6 is connected to both of these. That doesn't mean I can't go back and check out and do a C7 and continue working on the branch, right? This is actually common in Linux. We'll have people working on stuff. We'll merge them so there's something ready for release, and then you'll add a new extension to the modules you're still working on. So it will continue along the process. And then you can go back and forth just as before. So one of the reasons this is cool is that you now have a truly nonlinear development environment. I don't have to keep working on just one piece. If I think, oh, here's an idea, I go work on it, change it. When you're working in large-scale software, larger than you'll have to deal with in this class, it really becomes useful because you can say, oh, look, somebody broke this, or this is broken, and I'm working on something else. Can you fix this for me? So you jump to here, you apply the fix, then you go back to your code, and you're continuing where you are, even though they're often way behind. The release version of various things might be weeks or months behind the actual development version. And this allows you to jump back and forth and merge them. But sometimes it's easy to take code you just developed as the fix and incorporate it into the production version and see how that's going to go. So Git has some techniques to make it a little bit better for humans. It's called git tag, and it's really just a shortcut of a name. Instead of having to say git checkout FFOF, and remember that, you can actually just name them all and say git tag version 1, git tag version 2, git tag version 1.11, whatever you want to name them. The names don't matter, they're just strings, and it's just a mapping. But it can make that part easy. In this class, I don't know how much it'll matter, but Git has this idea of a submodule, which allows your Git repo to include other Git repos and automatically check them out and sort of keep them up to date. So when you run your make file, if the other code you're depending on changed, you can choose to upgrade it or not, and it'll keep track of all that stuff with you, but I'm going to skip over this because it doesn't really matter so much here. Okay, so working with remote. Everything I've described so far you can do entirely on your own local machine. But for turning in your assignments, we're going to want to see this in GitHub so we can see what's going on. And for those of you who, a couple of you had in your journals you wanted to check, send mail to the TA. I could see them, but I can't tell if the TA can see them because it depends on if you added them correctly. So if you wanted to check, do me and the TA send them, just send mail directly to the TA, can you check? Some of you definitely had problem with this. This is why part of the reason I realized I skipped over the lecture for this class. We want to go in and make sure that you know how to use Git. So if you don't know, your assignment is due next week, come to the office hours today, come to the TA's office hours tomorrow, right? Make sure you get through it. It's not that hard. And unlike some of the linear algebra questions, going to the CS tutors and asking them about Git is perfectly fine. If they tell you this is how Git works, you can believe them. If they tell you this is how your programming assignment should be done, don't be so sure. The CS TAs may or may not have taken this class, and I always change the assignments radically anyhow. So if they haven't thought about it, they might give you bad advice about how to do a particular part of the programming assignment. It's okay to go to them, it's perfectly fine, but don't say, well, I did what the tutor told me, therefore I should get full credit. That's not how it's going to work. We gave you an assignment. If you have questions about it, ask me, ask the TA. But for Git, that should work. They should understand Git well enough. Okay, so now we've talked about all these branches and the heads and everything. And we have a version that's local, and there's really the GitHub version, which I will use the phrase GitHub to mean the generic concept of where it is, not necessarily just the company. So I can do a couple of things. I can get changes from the GitHub by doing get fetch or get pull, which does a fetch plus merge. Get fetch is useful really only for very large projects where you want to look at things carefully before you start doing merging. You don't want to use the automatic merge process. But for this class, I can assure you, you just want to go ahead and do your merge. After you do some edits, then I'm going to do git commit am minus after merge, so I've done my merging. And then I can do a get push. So the normal sequence, in fact, it's such a common sequence in my lab for doing actual development. Many of the people in my lab have acronyms for them, like GP for get pull, GPH for get push, because you do them so often you want to minimize your keystroke, but you'll do that. Git has a couple of different protocols, your local file system, SSH, HTTP, and Git. Locally, so it's fast, it's useful, you'll do that, but mostly you're going to want to work with either, in my view, SSH, Git, or HTTPS. Which of those don't really matter. The one thing you know about Git with SSH is you can't do anything anonymous. Not a problem for this class, so that's okay, but you can't do any anonymous access. Actually, you can do anonymous. No, you have to GitHub account to still download it, so probably can't do much at all. The Git protocol is actually the fastest of all the protocols, but it runs on a non-standard port, so if you're trying to do this from home, your Comcast or whatever may or may not block it. It's therefore sometimes difficult to use. And HTTPS is actually the easiest to use. It is by far the most inefficient, but again, for the size of this class, efficiency is not a big deal. So for one-person projects, a local repo is enough. Well, this is actually, it's enough in one sense. It's not enough if you lose your laptop or your machine, so I don't actually recommend ever having just a local repo. My recommendation is you use Git access servers, because we already gave you access to those. Okay, so to go through adding a remote repository in Git, so there's two ways of doing it. I'm going to show you on the command line how I connect to something, and then I'll show you how to create it on the GitHub side. So on the Git, on the command line, I'm going to say git remote add origin and then the name of something. Right. So in my local repository, if I created it by doing a local init, I can actually now add that as a repository at GitHub. In this case, different ID. You have to put in the full path to your GitHub. So where are you going to get that from? I'll show you that in just a second. And then I can use commands to make the remote the origin, and then I can do push and pulls with respect to it. And I think that's it for this. Now let's go to actually create GitHub. So, this is weird. Now it's only showing one person in this class. Oh, it's actually only, that's why I started this. So one of your requirements for this class is that your repos be private, right? I don't want the other students in this class seeing your repos. If they're private but shared with me, then I can see it. So private means by default other people can't see it. It's one of the reasons why I actually created this class, T-Boult class, so you guys could actually be in it and, where'd it go? Yeah, I know, but it's like so right now I can see, whoever's that is, Michael Boult, your repo is still public. You will need to fix that. And now I'll go ahead and sign in. So, let's see, I'll go to I don't want to go to any of your repos. I want to go to one of mine. There we go. That's mine. So if I look in my repo, first, if I've done this remotely, I go over here if I want to create one. Actually, I'll show you creating in a second because it's a different page. Once I've created one, if I want to clone it, I can click here and it'll basically give me a string that I can copy over, and then on my machine I can say git clone and that string, and it'll make the local copy. Right, so that's where you can find the exact string of what you're doing. I recommend, until you get really good at it, you create your repos on GitHub and just clone them locally, not the other way around, because the other commands are a little bit more complicated, but it's pretty straightforward. There's also a desktop view. Actually, I don't want to do that because I've uninstalled it because it causes me problems. There's a desktop view which will basically let you browse files back and forth. Okay, and a number of you for the first assignment did this. You actually use the desktop view. I can get files, I can create a file, I can upload them, okay? Please, that's not the recommended file for doing this. It was sufficient for the first assignment, but going forward, especially if you're working in a team, we want to see the commits as they're happening, not just here's the final code, because we're trying to get you to use this tool properly. So don't just upload the file and create the file from here and upload it down and forth. Actually use the git commands that you're supposed to use. There are like file system versions where I can basically upload it and download from my file. Again, that's not the same as doing commits and showing the working on the code. So if I go back up here, to create a repository, I click on New. Okay? And when I go to create it, I can make it public or private. So if I create a repo and it says private, you're good. If you create a repo and it says public, then everyone else can see it, and we will have to take some points off because we don't want people copying from each other. You may not be the copier, but if you're a copyee, because they're copying from you, we're still going to take some points off because you're supposed to have made it private. Unless you think that's all just, well, you know, no one will ever do that. We already had a problem with assignment 1. So we want to. So this particular repo is actually public because I made it public for my other class. If I've made one public, or if I just want to check and I'm not sure anymore, if I go under settings, I can scroll down here and there's a button that says make, oh actually I did make it private now. This button will say either make public or make private, right? And I can go back and forth. If you're using your own GitHub account and you did not use the education pack and you're not part of Boult class, then private repos on GitHub are not free, unless you're a student. They set it up so we can do that. If you are trying to do your own projects and you want to have a free place, there's another big GitHub-like thing called Bitbucket. In Bitbucket, the default repositories are free and you have to pay to make them public. On GitHub, the repositories are free if they're public, and you have to pay if you want to make them private. So two very different models in how they want to get money out of them. Any questions on Git? Okay. As I said, if you do have questions, come find us during office hours. We can walk through some more stuff. One last comment probably worth mentioning. Git is a useful thing for actually doing backups. So if you're also a web developer and you're doing anything else, right, you know how cumbersome it can be to keep track of every edit you do on a website and all this other stuff. Or if you just have lots of files and you keep changing it for all your programming assignments, even though this was set up, we set up so you had access in this class, you can use this for any of your CS classes. You can use it for other student-based projects. And you can back up your entire directory into this. The first time you go to do the git commit of an entire, like, gigabytes of machines, it will take a long time. But after that, everything else is very, very fast. And it's actually faster than doing lots of other simple incremental backup processes. But if you're actually playing with it for a software versioning, right, you're going to use this in your other classes, so just go ahead and get used to that. It's also really useful for configuration environments. So if I'm playing with things like Apache, web development, or whatever, I can literally have multiple different environments, check them out, and then keep track of each of them as though I was on this machine, I'm on that machine, and then, so you do all your development locally, then you connect to your web server that you're actually doing stuff from and use to git pulls to update stuff. And it keeps track of all that information to make it very easy to keep track of all of your stuff that's pretty much the same. So, okay, so now we're going to move on to, I'm going to start with chapter 6 because I want to make sure I get through everything. And if I have time, I'll go back to do some chapter 5 stuff. So first, a comment. I saw, yes? Yes. So next Monday. Okay, that's why you're confused? Good. It's confusing me. Let me go check. That's not what I said in the assignment. Yeah. Okay, so it does say the design doc is due, and so I will stick with that. Originally, Program 2 was going to be much more extensive than it was, and then I decided to move some of the stuff I put in Program 2 into Program 3, given how badly things went in Program 1. Lots of people were struggling, so I didn't want to push the programming quite as much, and I did not update the syllabus. The assignment says the whole thing is due, because it's actually now a simpler assignment, but I will still be able to make that work. One of the reasons, in fact, you had less reading and stuff this week was because the programming assignment was going to be much more extensive. And I figured better give you some time so you can actually work on the programming assignment. And then I didn't make the assignment as extensive. Oh well. So no, next week I want to see here is the core level of the code. It doesn't have to actually all work, but you should be turning in a design doc that says, here is how I'm going to represent lines. Here's how I'm going to represent the lines over history. Here's how I'm representing the grid, which is an array. Here's how I'm answering the question, should this cell be on the line or not, right? You don't have to have all the code working. You're just going to describe sort of the concepts, the basic data structures, and the math you're going to use to represent it. Does that answer the question? If you're not sure how to do stuff, you can also finish the entire program next week because it's not as big a program as it was going to be. But all that's due next week is the design doc. The design doc then I will make do. I'll modify the online assignment. I apologize for not noticing this. I changed it when I made the assignment, but I forgot I'd already put stuff on the syllabus, and I'll just live with that. Other questions? Say again? Word document, raw text document. When you're working in your design documents for your code, right? I find it best to actually think of it as it's a text file, so that it's part of my program. It's like literally like I start doing the design, you write it all down, you work through it. But if you want to do it in a Word document, that's fine. My recommendation is you keep your design docs in a format that is editable by your code editor, so you can refer back and forth to them easily, as opposed to having to open up some other tool. But that's your choice. Other questions? Well, So let's see. Any questions from the Chapter 6 reading? Chapter 6, I think most people found relatively straightforward. This is now material that, by the way, we're going to start the previous weeks. We were covering stuff that largely, much of it would have been stuff you did in high school, 2x2 systems, solving simultaneous equations. You may or may not have seen Cramer's rule, so it started slowing down after that. But the first stuff of like vectors and points and lines, people should have seen, but not everyone has. So I went fast enough so that everyone could get caught up, but not so fast that they fell completely behind. We're now moving on to stuff that's a little bit different in terms of very few people will have talked about affine transformations in high school or anything else. So now we're going to go ahead and start on our clicker questions. So what is the closest point to the line R? So there's a line and a point R. What's the closest point? Oops, it's on. Does anybody remember what's on the back?
I didn't sign up for a new one, but it's still just showing me this. Thank you.
Okay, and by the way, if you haven't figured this out yet, this isn't from Chapter 6. So if you're rummaging through your notes trying to find where in Chapter 6 is this, oh, I forgot to start the poll. And go ahead and work with a neighbor since lots of people already are, so it's fine. Mhm.
see here. So every time I try and join, it will just tell me back to the same screen.
It's odd, is it showing you results you had from before?
Yeah, exactly, but it's still.
So you're in your account. It's actually,
And it's sent. So I can see it.
figure out. So one of those students also did something. I'm not sure why. See if you can try, because you like had the account and it went invalid, right, and then you paid it. Try deleting the class and adding the class back in. See if that works. Okay, I'll give you another 30 seconds. Okay, last call. Oops. No. Okay. Okay, so how did people answer B? It's our second most common answer. Can you speak up? Okay, so 0, 0 is on the line. You can put that in, but 0, 0 is a point that is. So, what was the process? Just putting in it. You can't put 0, 0. You can put in -1 for t to get that. But why do you think that's closer to the line, the closest point on the line? Just a math error. Okay. So, problem like this again. Eventually, we're going to get to the point where you can't draw stuff because it will be an ND. But for 2D and 3D, you can think about this, right? So, if I draw my line, so here I have the point 1, 2, 1, 2. Here I have the point 2, 2, and then I have the vector that's going up by 2 over 2. So if I go over, that is like that. And so here's my line. Okay. So in one sense, the point 0, 0 is on the line, right? But I'm asking, what's the point on the line that's closest to the point R, which is 0, 2? Okay, graphically, where do you think this point has to lie? What's the constraint we need it to have? Okay. It has to be perpendicular. The closest point on the line is always a perpendicular at an angle. Right? So that's a beginning of a constraint. So just graphically, it couldn't be 0, 0. In fact, How many people solved this graphically and said it's got to be 1, 1? Okay, that's okay. But how many of you, when you did that, also remembered that there is a formula or a way of computing it? You can actually go through this process. That's good. So you want to go through the calculation. So the correct answer is A. That calculation is compute this vector, the perpendicular vector, which has the orientation -2, 0. So that's this vector. Sorry, that's not this vector. Well, actually, that's this vector. So this is W is equal to R minus P. That's the point on the line. And then I'm going to use V, which is the vector of our line, this side, and I use V dot W divided by the norm of V squared, and that gives me T equals 1/2 that I can plug into the formula. So if you just remember formulas, you can do it that way. You can derive this by knowing what this point is, that this is a 90-degree angle, so all of this now falls back to trigonometry, and you can again compute what this point has to be, right? Which actually is how you derived that formula for T. Okay, another pair of points. Given X and R and an angle alpha equals 90 degrees, find the rotation of X by angle alpha about the point R. What is the X prime that results from this? Okay, I'll give you another 30 seconds. Most of them in. Okay, last call. Okay, so most people did get this one. So the correct answer was D as in David. So this is a classic rotation problem, which a number of people said in the journal they struggle with, right? So the basic idea of how to rotate around an arbitrary point is you know the rotation matrix for the origin. So I take the world, I translate it, so the point I want to rotate is at the origin. I rotate, and then I translate it back. So that as I get my outcome is x minus r, rotated, and then add back in r. Right? So move it, rotate it, put it back. And that allows me to rotate around any arbitrary point. And the rotation matrix is the standard cosine alpha minus sine alpha, cosine alpha. So we're, in this case, alpha is 90 degrees. That gives us a rotation matrix of 0, minus 1, 1, 0. And I first subtract x minus r to get 4, 3. Multiply that, add in the vector 5, 3 again, and that gives me 2, 7. To get most of the other answers, you have to do either a small algebra error or, I don't know, I guess. So, none of them had any particular meaning, like you forgot something significant. So, did anyone get them for a particular reason? I mostly just made up things with 2s and 7s and changes of signs, but yeah. So you rotated this way, okay, instead of that way. What answer does that give you? C? You get C? Okay, well, the rotation is by default whatever direction this is. Your point of view, clockwise. Okay, so next one, again, this is from the journals. People had some problems with doing Gauss elimination for inversion, which is necessary for some of the chapter 6. This is from chapter 5, really, but I want you to go ahead. So if this is the matrix you want to do inversion, you want to invert, using the steps of Gaussian elimination, which is shear, something, or shear, a bunch of shears or whatever, which of these 3 sets are the matrices you get doing Gaussian elimination to invert the matrix 4, 4, minus 1? Minus 1, 4. And yes, I know for 2x2s there are formulas for inverses and whatever. We'll talk about those in a bit. But when we get to higher dimensions, those formulas will no longer exist. So we want you to get used to thinking in terms of Gaussian elimination. And you can work with a partner on this. I'll give you another 45 seconds. Okay, last call. Okay, we got a pretty wide distribution on this, so we're going to talk about it, and then I'll give you another chance to work on it, because that's not up to date. What's the first step for Gaussian elimination, Brad? So you don't know how to do Gaussian elimination. Okay. In the back there, Anthony Abbott. What's the first step of Gaussian elimination? Over there. So you make it 0 below the diagonal, right? So our goal is to make it upper triangular. Actually, the first step is to always check if I needed to pivot, but we'll give you credit for that one anyhow, because this one doesn't need to pivot. The larger number is on the diagonal, so now we want to make it 0 below the diagonal, right? So given that as a hint, now let's just figure out the shear that makes it 0 below the diagonal. We'll give you another chance and chat with a neighbor if you really don't have any idea how to do the shears. We're going to multiply by a 2 by 2 matrix such that the lower diagonal -1 disappears and becomes a 0, and we'll get some new matrix from that. Okay? And I will tell you now, if you can answer what is that matrix, you can answer this question, because the answer is not E. And by the way, more than half of you were right last time. It's not like you have to reconsider if you think you really did it right, but some of you did not. And if you got an answer, there should be a way for you to check it. Right? doing Gauss elimination. You have some matrix. This is what we have up there. And so we have our matrix 4, 4, minus 1, 4. I'm going to multiply it by something with the goal of getting something, well, A, B, 0, C. Right, so I'm going to multiply this by this to get something that looks like that. Now, there's 3 matrices here because when I do Gauss elimination, to get an inverse, if I have A, right, I start with A equals I over here, I, and then I find a shear matrix, S1, S2, S3, and so on, until I've reduced this side down to the identity matrix, and then this side will equal A inverse. Because I've gone through that process. So that's why there's 3 matrices here. A student in their journal said they didn't understand how you get multiple shears to get to the identity matrix. I'll go through all of that when we go over the answer. So I'll give you another 45 seconds. Yes, Ryan. So matrices are written in the order you would multiply. So if I have 3 matrices and I put A over here, right, then I'm multiplying, they associate, right? So I have A times these, right? I can multiply these in any order I want times it. I can multiply these, but this, one of these end ones is the shear matrix we're talking about. When I talked about shearing, you can make this angle 0. That would be the rightmost of those matrices. I'll give you another 15 seconds because I was off wandering on the. Last call. Okay, a little better, not much. So how are you going to check your answer on this one? I said you should be able to check your answer. How can you check? At least the first part of your answer should be pretty easy. You can multiply whatever. If you chose, say, C, I can multiply this 4 by 4 by that 4 by 4 and see what I get. So the correct answer for this, even though I had all these matrices, right, and I'll go through the whole process, right, to answer this question, you actually only have to be able to do the last matrix because they're all unique. Right? I could have made them all the same. That would force you to go to further levels, but that just increases the chance for algebra error. So let's go through how you actually solve this. So you want to find a shear matrix that shears the first one, so the bottom left-hand side is 0. Now, there's a formula in the book, and if you're good at remembering formulas, remember the formula in the book. If you don't remember formulas very well, I don't. I just derive them every time I need them because I know the basic principles. I know I want a matrix that's going to make the bottom left-hand go to 0. And I know it's a shear matrix, so it's going to have a form of 1s along the diagonal, a 0 in one place, and some number on the other. Okay, now, if in high school you actually did multiple simultaneous equations by figuring out multiply the first row by something and add it to the second, right, or multiply the second row by something and add it to the first, that was also, by the way, doing a shear matrix. So maybe that'll help people understand how to derive it if you can't remember it. Because if I think about what is the shear matrix I have here, 1, 0, 1/4, 1, the 1/4, 1 is really saying multiply the first row by a quarter and add it to the second row. Okay? So if I take the first row, 4, 4, I multiply it by a quarter, I get 1, 1. Now I'm going to add it in the bottom row, and I'm going to look at that. I'm going to have 1 minus 1. I'm going to cancel out. I'm going to get 0. And for the bottom one, I'm going to get 4 plus 1 is 5. Right? So I wanted to give you a different way of looking at it because from the journals it was clear people like this is unlike anything you'd seen. It's like, no, if you did 2x2 equations in high school, and you probably did, this is actually very much like it. We're just doing it in a more structured way. We don't say multiply this equation by that. It's like it's implicit. The matrix form is a way of talking about multiplying rows and by values and adding them back together. So that gives us the first shear. Now, if I really want to get to do Gaussian using Gaussian elimination to get it into full inverse form, now I have to get rid of the upper right-hand column. Now I have to do the other shear to get rid of the other column. So I do that by doing 1 minus 4/5, 0, 5. Where did I get the 4/5 from? Well, I just looking at this column, I said I have to multiply the first one by the second one, the bottom one, by something, and add it to the first one. Right? So 4, I'm going to get 4 minus 4/5 allows this to then cancel out, and I get 4005 as the next stage. And then for the last one, I want it to be the identity matrix, so I have to scale it by 1/4 and 1/5 to basically multiply the columns or the diagonals to get them back to 1, 1. So that gives me the answer D, where each of these matrices is then written out. Any questions on that? I can guarantee your midterm will have a do Gaussian elimination question. So if you struggle with this one, do a few more practice ones. Okay, so just for fun, what's the inverse of the matrix? A equals 4, 4 minus 1, 4. And if that matrix looks familiar, that's because it's the same matrix. But now I want the actual inverse. And you can work with the neighbor. These are calculational ones. Give you another 30 seconds. Okay, last call. Okay, so most people did get this one. So there are two ways, well, maybe three ways to solve this. So, Brittany, how did you solve it? Okay. So that's the second most common answer was D, and the way you approach it. So what is the property of the inverse matrix? So we'll go for Olga right next to you. Olga, what property does the inverse matrix have? So that's the identity matrix. The important property of the inverse is that if I have a matrix A and I multiply it by A inverse, that's equal to the identity matrix. Right? So I'm going to find a matrix such that when I multiply it times A, I get the identity matrix. So who got a different answer other than D? Right corner. So no. Gotta understand my chart here. Oh, you're not there. What's your name in the corner? Jeremy Wilmer. Oh, okay. Jeremy. Okay. Go ahead. E. None of the above. That is the correct answer. So the two. No, you were just here. Okay. So there's two ways of doing it. By far the slowest way of solving this problem is, but since I just gave you the answer here of what were the elements of Gaussian elimination to make the inverse, I can take those three matrices and multiply them. Using the fact that I just said up here, if I multiply all these by A and I start over here, I get the identity matrix. So all of these times A gives me the identity matrix. Then this must, when I multiply all those out, they give me the inverse. So if I multiply all those out, just lots of 2 by 2 matrix multiplication, good practice for those who have to go through that. You get 4 over 20 minus, 1 over 20 minus 4, right, which is not any of the choices I gave you. Okay. Now, there actually is another way of solving this. Did anyone solve it? Did anyone solve it this way, by the way? You actually did the full-out matrix multiplication? Okay. Anyone solve it a different way? Yeah. Okay, so you don't multiply quite by the matrix. So it's 1 over A times D minus B over C. And then in the matrix, I swap A and B. So I'm going to start with the matrix A, B, C, D. I swap these two, and then I put the minus signs of these two. So for a 2 by 2 matrix, there's actually an explicit formula for the inverse, which is actually 1 over the determinant times this, which is called cofactor expansion of it. We swap these around so I can fill that in, and I again get the same answer. Okay, so that's a easier way for 2 by 2. If I ask you to do the 2 by 2 and I don't tell you how, my recommendation is this is one to remember, right? So this is actually a formula I do remember because you do 2 by 2s often enough, and this just saves so much time instead of deriving it by hand. Deriving it by hand would be doing the Gaussian elimination process. I could write a program to do that, but I don't want to do that by hand very often. Anyone solve it any other way? There was one other way of solving this, which is not what I recommend, because on the midterm I would not ask multiple choice questions. But again, in class, one of the reasons multiple choice questions is it increases your ability to check your answer. So one way of answering this was actually to just multiply this times each of these and see if you got the identity for any of them. And you don't. So that left you with E. But that was an exhaustive search process. But you do 4 matrix multiplications, you can get that through. So. Okay, quick engagement question. Okay, let's call on that. Okay, now given that distribution, we'll go understanding why people were disengaged, since there were some of you disengaged. Okay, last call on that. Okay, so that one's pretty clear. That one's going too fast. Okay, so I will see if I can. So if there's a balance, a couple people said it was too slow, but if it's balanced, I keep going at about that speed. If it's more people say it's going too fast, I will slow down just a little bit because I don't want to lose too many people. Okay, so now let's go to the next hard questions. These were the questions that lots of people said were difficult when they were trying to deal with this in their journal. So we want to make sure we go through these. So T is a triangle. You can work in pairs. With those 3 points, T prime is the new triangle. You want to map triangle into the second triangle. Find the affine map. Now, there's actually more to the map than that, but find the affine, the matrix in the affine map that takes T to T prime. So I see some people stirring off blankly. How many people have no idea how to solve this? Okay. So it was in chapter 5, 6? 6? 6, yeah. It was in this chapter, so... page what? 126. But just a reminder, during the exam you will not have your book, only your notes. Okay. Still going slow. I assume, are people still working on this? Okay. Okay, so our answers are all over the place, and even though everyone's not there, I'm going to start talking about, just make sure everyone's, because you didn't have your book, and depending what you had in your notes, right? So you're trying to figure out the map that's going to map one set of the triangle, one triangle to the other. So if I think of my triangles, and I'm actually going to draw my triangles sort of funny, I'm not going to close them. And this is not necessarily the right numbers for this thing, right? But I want to map this triangle to this triangle. Right? So one way of looking at that is a triangle has two vectors, right, which I get from the 3 points. And I want to map this vector to this vector, and this vector to that vector. So if I think of those two vectors, right, then I can think there is some matrix A that maps V1 to V1 prime and V2 to V2 prime. Now if I actually, since those are two equations and A does it for both of them, I can actually write them next to each other, and I can write A times the vertical concatenation of two vectors V1, V2 equals V1 prime, V2 prime. Now, these are two element matrix columns, so when I put these together, this is also a matrix. So this is actually in matrix form, A times the matrix V equals V prime. And if I want to get the solution to that, knowing the fact that if I take not just A prime equals the identity, but so is A inverse equals the identity matrix, I can post multiply. I can put a V prime on this side, and this goes away to become A. I can put a V minus 1 on this side. The equation's still the same. As long as I multiply both sides of the equation by something that's well defined, I can keep doing that. So that tells me that A is equal to V prime V inverse. Now, if that's not the path you're going down, there are some very brute force ways of trying to solve this, but that's the linear algebra way. So it's still open. I just wanted to give people some hints because it was clear from where things were going, it wasn't going down the right path. So you're not multiplying. So you're talking about this formula? This formula? Mm-hmm. Okay, so it's just a formula to give you a matrix. So it's 1 over AD minus BC times D. Right? So I'm not. You're talking about multiplying stuff, right? So, yeah. So
AD. So
okay.
A multiplied by D.
Mm-hmm. Mm-hmm.
BC, and 1 multiplied by -2 is equal to 2,
yep.
Which is subtract from -10, to give you 1 over -12.
That's right.
Not the answer, so did I mess up something?
Well, that's so. This formula is this. So the formula was V prime times V inverse. You only have the inverse so far. You still have to multiply. You have to multiply that by V prime.
I did, and I got this matrix right here, which I know isn't right, but.
Okay. And then you multiplied. What'd you do with this guy?
I left him out front.
Yeah. You can leave him out front. That gives you an answer to it. Okay, I'll give you another 20 seconds. Okay, last call. Okay, so the process for solving this is first we have to get those vectors. I didn't tell you exactly how to get the vectors. I implied it here, but I get the vectors by taking a point minus another point to get each of the vectors. So in this case, you're going to use A1 as the base. So I'm going to take A2 minus A1. I'm going to get 5, 2 minus, I'm going to get 5 and minus 2. 5 minus 0 is 5. 1 minus 3 is minus 2. That gives me my first vector. And I forgot the transposes here, so I apologize. I should have written them vertically, but I forgot. V2, right, is 1, minus 1, minus 2, minus 1, minus 0, 1, minus 3, and so on. V prime, I do the same thing. 1 minus 3 is minus 2, 5 minus 0 is 5. 1 minus 3 is minus 2, minus 2 minus 0 is minus 2. So that gives me my 4 vectors. I make my matrices V and V prime out of those. Now in the formula, I need to take the inverse of V. Oops, back here. So I get 1 over 12 minus 2, 1, 2, and 5. Again, if I use that inverse formula, I put that together. And then I have to multiply that times V, and I get the answer C. So there's lots of room for small algebraic errors as you go through all of that, but hopefully, even if you follow the process right. On the midterm, there won't be multiple choice. It'll be, you'll work through it. You'll get partial credit if you make a small algebra error. I don't take off much for those because I make them all the time. Any questions on this one? I can't hear you. There's a humming back here. Negative 12. Oh no, did I get the signs all wrong? So, oh, yeah. Okay, well then the correct answer would be E. So yeah, so if it's negative 12, I will check. Again, that's, especially when I type things, I sometimes drop an item as I'm typing them over. So maybe the answer is then E. Let me fix this. Yeah, no, I can see it when, and somebody else came up and asked me that, so I wasn't paying enough attention. But okay, so the correct answer, which actually was the second most common answer, so pretty close, was the E, none of the above. I don't know, given how bad that was, maybe I'll just give everyone who had C or E. I'm not sure how to do that in Canvas or in this clicker version, so if I can, I will. If not, we'll just give everybody a point for that one. So actually, why don't we go ahead and take our break now, because I went a little bit longer. Be back by 9:55, so 5 of 10. Get it to work?
Yes. It was just being mean to me.
Okay, well, somebody else had the same problem, so who else had the same problem?
So that last one, I didn't notice that E was an option. So I just picked C because I assumed that you just accidentally dropped the negative off of it.
Which is what happened, but yes.
Yeah.
But so I've learned my lesson when I do these, especially I did this like last night at like 10 o'clock. It's like, I'll put the none of the above in case I made a small algebra error. There's always an answer. So I did. I can't answer like in terms of your programming skill, right?
Yeah,
So
well, right now I changed my major my sophomore year, so I never did any programming before then. So this might like last year and this semester. This is my first time programming.
So you're taking 1150, 1450, two programming classes?
The like just like
Oh, you're a games major. So how many of your games? So you took like just the drag and drop class, or
I took
C sharp?
C sharp, but I haven't done like matrix inputting stuff like that. Or like
Well, no one is, right? No one is expected to have done matrices as programming, right? They might have done it as math in high school, but from a programming point of view, no. I
So
don't
what's
expect.
my best thing of like approaching like this next program? Because I don't know how to like approach it all. I look online like to see how you make a line, which was like draw a line instead of like creating a grid.
Right. So the grid is an array. You're gonna make a 2D array.
Make two.
Array.
I know how to make arrays.
Right. Yeah. So 2D arrays, we have like X and Y or I and J, right?
So all I did
That's the grid, right? And then you're going to figure out how to how to basically make points on the grid flip from 0 to 1.
and that's based on someone's inputs by the keys or the mouse buttons.
Neither, right? This is all text-based, right? So, because making you do all the mouse clicking work is a lot more complicated, right? So, this is, you're going to read it, there's a text file that was in the syllabus, right? So, let's go back to that. I was actually already there. So, like, there's going to be a file that's going to look like, I'll just open this one up, right? It's going to look like two numbers, n saying how big is the array, so it's n by n, and then k says how many history I have to keep. And then it's going to say, I want 0.1155. So that's a 5 by 5 grid. So I want to draw a connection from 1, 1 to 5, 5. So you're going to connect, you're going to fill in those points and say that's what drawing the line is doing. So one of the things that you might do is, and I don't know who else you know in this class, but like, you're allowed to work with a partner, especially if you feel you're okay with the math, but you're struggling with some of the programming. Find somebody that's good with the programming and struggling with the math, and the two of you make a good pair.
Yes, sir.
So you can actually use break as a time to be like, hey, I'm looking for a partner. I'll give you a chance at the end of this to stand up and say, hey, I'm looking for a partner. We want to work together.
Oh, very easy.
Okay?
Thank you.
Yeah. John?
So I sent you an email. I don't know if other people had the same problem, but I never received the email inviting me to the Boult class GitHub. I did for the education pack, but it never let me join the actual class.
So I will go and do that again. Let's see. So it probably went to you. So it doesn't come from me.
Yeah.
It comes from GitHub.
Right. I searched twice and
Okay. So JS. What's your email?
JSchwan, so JSCHWAN 2 at UCCS.com.
Said you had an invitation, but send it again. Yep.
Okay, thank you.
Check right now.
So on the program files, the text files that you were given to us, there's random periods in
Not random. Just sometimes numbers have one, digits and decimal digits. 1 point whatever.
So is it like a 1.0 or is it like 1 point? Because it's like 1.235.
No, since there's nothing after the point, it's 0.
Oh, so it's just a random point?
Well, it's like 1.0. It's just,
Okay. Because I was just like, do I read that as another thing? Okay, that makes sense.
It's messing with you a little bit in the sense that you have to read and ignore decimal points, but somebody could say 1.0, right? So
Okay.
it would still be allowed.
Okay, because I thought it was just like right there. I'm like, I don't understand. Okay, that makes sense.
So last week I was asking if I could make my repository my own private thing, but it looks like it got marked down for not uploading to the class GitHub.
You shouldn't have lost points for that as long as the TA could get to yours. If he took off for that, send him mail and I'll check. He'll check with me. But yeah,
That was the comment you wrote anyway. And it also looks like the invitation I sent out to both you and TA, both of them haven't been accepted yet.
Okay. So let's see. What's your email?
So G Atkins.
Oh, actually, so what's your GitHub?
Oh, my GitHub.
What's the, you have to get
It's yeah, G Atkins 2 is my GitHub.
Okay, let's see. So I don't see an email invitation, but if I click on the right link, it'll probably just show it to me. So go to the journals. G. Atkinson?
Mm-hmm.
Come on, show it to me. I don't want to just change the grade. I want to see it. Dang it. Okay, accepted. And now I will send mail to Chris and make sure he does it. Okay, and you're sure it's private, so.
Yeah.
Okay, you're good.
I emailed you and the TA just like about the program one. I like mine, like the first part of it, I submitted the wrong one. And then you just said like upload it to the GitHub. So then
Well, no, so if it had been uploaded to GitHub, we
Yeah.
would have seen that you had done it on time.
Oh, well, I just did like all the files. So
And they were uploaded after the deadline. That's what that was. So if he took off points, because we talked, I don't know if it was or not. I told him to check.
No, it was I uploaded it before the deadline.
Okay.
But then like after the grading, he said like it was only 10 lines.
Yeah.
So then I uploaded it. Like I re-uploaded it afterwards to see if I could get like a regrade of it because I uploaded the wrong first part of it. So it was just saying.
Okay, so we can't give you full credit because
Yeah,
they've easily
yeah.
done it afterwards. So send us both mail. Now I understand. It's like I told him, like, you know, look at what is it. You know the dates because that's why it's in GitHub.
Yeah, of course.
So if you uploaded it after that, which is what he told me, it's like, well then you know it doesn't count for that. But if you want it graded, we can give you some points for having done it. So okay.
Yeah.
Okay.
So just send you like.
Send me mail again so we don't forget.
Okay.
So in the input that you gave on the project too, I noticed there's like periods, and I'm not really sure what those are for.
Like 1.0 is a
No, just 1 point, and then
well,
nothing after.
1 point is a number, right?
I guess, yeah.
So it'll push your parsing of the number file a little bit better.
Okay.
I had a question about program 1. I emailed the TA. Do you know if you can get back to me on that? Because he made a comment that doesn't make sense to me.
Okay.
He said my matrix 5 is either unreadable or incorrect. I'm like, well, what do you mean by that? And I pulled it up. I was showing a couple people. They're like, no, that looks like what I did. So
Okay. Don't know. Send a mail. CC me. His office hours are tomorrow during the syllabus, right? So
Okay.
you can maybe stop by and ask him then.
well, I'll be at work, but
Okay.
will he
Just send
be
him
able to reply to my email
Yes, yes,
tomorrow?
yeah.
Okay. Sounds good. Thank you.
Okay, we're gonna get started again. Okay, so we're gonna do a couple of quick vocab kind of questions. Vocab is a part of what we have to cover, and there's a lot of these to go through, and these go quick. So 30 seconds for these. Okay, I'll give you another 10 seconds. I guess some people might be back. Okay, so the correct answer for this was translated, B. Okay, it actually isn't transform. Transform is a phrase we generally use to mean it's changed shape and whatever. Translation is a rigid body transformation. So maybe there's some value to that word transformation, but it's not transported. That's a Star Trek term. But I wanted some trans in there, so they were all trans. Okay, so another rotation point. We did one of these earlier. We'll just make sure we get this nailed because some people said they were struggling with these. So what is the point of rotating x 90 degrees around the point R? It is rotating clockwise 90 degrees. Okay, I'll give you another 30 seconds. Okay, last call. Okay, so most people got this, right? As we said before, we translate the point back, multiply by a matrix, and rotate it to rotate it, and then translate it back out. So the correct answer is B. We take the rotation matrix, which is again 0, -1, 1, 0, because we're rotating by 90 degrees. And by the way, midterm, right? I will always choose things that are simple in terms of what those matrices are. They might be the square roots of 2 for 45 degrees, but nothing weird where you need a calculator to know what alpha is. And so we get 3, 4, -1, 1, which is the point when I rotate about, 2, 3, rotate it by 90 degrees, and then remember to put it back. I did not give you the choice of the tempting one that's in the wrong place, but we'll do the next one really quick. Try this next one on your own, because it's like the last problem we just saw. But we'll give you a minute for this one, so we want to go through these quickly. Okay, another 15 seconds. Last call. Okay, so most people are getting these right. If you're still struggling with these, practice some more. There definitely will be rotate, point around point kind of questions. The correct answer was C. We take x minus r, we get minus 1, 4. We multiply that by our matrix A, which is 0, minus 1, 1, 0 for our rotation matrix, and then add back in the 3, 1, and I get 1, 0. So I don't know how to get the other answers, but there were some people, besides guessing, there was nothing intentionally distracting in this one. Okay, another inverse question. Given A is the matrix here, what is its inverse? Try and do this one on your own. Give me another 30 seconds. If you've solved it, you might think about how you check your answer. There's a couple of you need to check. Okay, last call. Okay, so most people got this one. The correct answer was A. Again, using the 2x2 matrix formula or inverse formula, 1 over AD minus BC, which is the determinant, times swap A and D, negate B and C. You get that answer, which really starts like that. You have to multiply some stuff out, but works out to give you the right answer. Okay, blast from the past. Given U, what is the orthogonal projection? What is the matrix that gives us the orthogonal projection onto U? So a hint, this is from chapter 4. If you're wandering around your notes, where do you look? You shouldn't, by now you should have known where it was from, but so I'm asking, what is the matrix that will do orthogonal projection onto you? So yes, there's a second part. There's the matrix. I'm asking you for what is the matrix that will project anything onto you. So U is a vector. And I want to know the matrix that will project, well, this is actually probably not correct. The matrix that will project anything onto what that vector looks like. 2 over the square root of 5, 1 over the square root of 5. So I have a vector that looks something like that, and I want to know what's the projection matrix that gives me the orthogonal projection. You can work with your neighbor on this one. Give you another 30 seconds. If you're still working, I'll give you a hint. For many people, this question was super easy. Okay, last call. Okay, so we were looking for the orthogonal projection matrix. Which of these answers is a matrix? D. Everything else isn't even of the right form. Right. So that's why I said for some people, there were people who answered this question almost right away because you look at it, it's like, Well, only one of them is a matrix. I don't have to compute it. There's no E, none of the above to really mess with you. You have to do calculations. But how do we get that orthogonal projection matrix? Does anyone remember the formula? No? A1 equals okay, that might work out. I'd have to think harder about that formula. Let's go for Ryan. Right, U times U transpose. Right, so U transpose gives me a projection matrix, right? So I take U as a vector, I multiply by U transpose, which might work out to be the same as what you said. I just have to think hard about all the symbols. So now, the other reason I want to mention this one, and I put this in, is because one of the students in their journal said they were struggling with how do you find that orthogonal projection to a line, which is I know from last week or weeks ago, but that's why we started with that question. So here's a different way to solve what is the closest point on a line. How do I use this to find what is the closest point on a line? Right. Well, it can be useful for reflecting over the line. We'll get to that in just a bit, but that's another related question, because that's like how first I find the closest point on the line, then I just double it and get there. But how do I use this idea of orthogonal projection to solve for what is the closest point on a line? I know you have the answer, Ryan, but we'll see. Anyone else want to? Jono? Don't know? Okay. So if we think about what this is doing, right? I want to project orthogonally to the line, right? What does that mean? That means I'm projecting perpendicular. So if you give me a point, and I want to actually answer what point on the line is it, right? There's a formula that the book talks about. You can compute t, and then you can do all this work to figure out what t is and put it back in the line, right? Or you can simply say, okay, if this is my vector u, take u transpose. That gives me a matrix. I multiply this point by that matrix, and it gives me this point. Now I have the point on the line. And if I want to figure out how to reflect the point around a line and come over here, once I know this point and this point, I just subtract them and I add it back to the other side and flipped it over the line. Okay, so I don't know why the book doesn't present that one as one of their techniques, because to me, this is why, like, I can remember this formula. I'm not sure why, but maybe because it has only three symbols, U transpose. It's pretty simple how to get there. And then I can use that to get to any of the other nearest point kinds of questions. Oh, right. So this U transpose actually has a name. It's called the outer product, and somebody used that term in their journal. I actually don't mind if you guys are reading ahead. You want to read chapters 12 and 13 because you're really interested in homogeneous coordinates, because you're really into graphics, whatever. That's okay. But when you're doing that, make sure in your journals you talk about this week's reading, right? Because I have students that are clearly not, their journal entries have nothing to do with what you read this week. It's either from chapter 1 or chapter 2, which is like a long time ago, or chapter 11. Those aren't really what we're supposed to be reading. So reading ahead is perfectly fine. Asking questions is perfectly fine. So somehow relating things to outer product, which was the journal question. Is it okay if we use an outer product for computing the reflection of around the line? It's like, that's perfectly fine. Right? You don't have to do it the way the book does. So, quick engagement question. Okay, now, since again we're still here, okay, why disengaged for the 9 or 10 of you that were? Okay, so last call on that one. Okay, now we'll go to a real question. The inverse of B. Yeah, another 45 seconds. What? There's only 5? Okay, last call. And in fact, for those of you who recognize it, not only was there a 6th answer, it was actually the correct answer, B. So again, this is straightforward. Multiply by 1 over the determinant, swap A and B, negate B and C. Okay, so now for some questions that some of you say you're struggling with. What happens visually, right? And I want you to get some intuition. So I want you to figure out how to describe the map that maps this one to that one. Okay, I'll give you another 15 seconds. Okay, last call. Got them all in. Okay, so most people did get this. So one of the questions that people sometimes struggle with is, so is it a rotation or a reflection? Okay, that's just a question people struggle with looking at things like this. So how do you tell if it's a reflection or a rotation? I mean, you can just try and do everything in your head, but there's actually something distinctive about reflections that make them easier to answer. Right? So this particular drawing makes it easy, right? So reflections change handedness, right? So in some sense, the bird is looking left, right, in the one on the left, and is looking right on the right. No amount of rotation will make the bird look from left to right. It's got to be a reflection in there someplace. So you can get rid of A and C. Then it's reflection about what? So why is it not a reflection around the E1 axis? Right, so sort of the tips of its wings would be pointing down or whatever, right? So reflections around the axis can't also look like a rotation. So this one was a little tricky because it's got what looks a little bit like a rotation. So the correct answer was E, a reflection around the x equals x, x1 equals x2. We can do reflection around any line we want that goes to the origin, and they will give you different things. Okay? Given that you have some affine transformation that maps the phoenix to this shape, what does the inverse map do to the phoenix? So A is a map that maps the phoenix into this. What does the map A inverse do to the original phoenix? Okay, so we got a pretty wide set of answers here. Let me ask the question in general. So if I have, what does the inverse map do to this one? It puts it back to that. Right, so if you're struggling for what does the inverse map do, a map from this to this, the inverse map from this back to that. And now I'm asking you, though, instead of applying the inverse to this, apply it to that. That's right. I'm asking, there is a affine transformation that does that. I'm asking for the inverse of that. So yes, so you are correct. It is a shear. It might be a shear with a translation. It's hard to tell, but it's at least a shear. And so you're effectively looking for the inverse shear. That's a sheep with a sweater on it. Okay, last call. Okay, so if the original matrix does this, the inverse does this, right? That's the way it is. So an inverse shear applying this, right, which is shearing it this way, will give us D as the answer, which most people got. Okay, another quick question. Do this one on your own. Using Gauss elimination, what would be the first step of solving this system? If there's no calculation in this, I'll give you another 10, 15 seconds. Okay, last call. Okay, so A is the trick answer that many of you fell for, since A1 is already on E2 do back substitution. But for formal Gauss elimination, you can't do back substitution for a lower triangular matrix, only for an upper triangular matrix. So the first step, the correct answer is to pivot, which was E, none of the above. Right? You swap the two rows, then you can do back substitution. It's true if you're as a human looking at this saying, yeah, I can solve this system because it's easy, right? But when you're going to write code, you want to have really straightforward processes. You check something and you always do this, then you do this, then you do this as a process. Ryan, question? No, this is definitely solvable, right? So, I'm not sure exactly what you read in the book, so read it out. What's it? Right, so that's true only after pivoting. Right? After pivoting. So if I pivot, I'm going to put the largest item up top, and now there won't be a zero on the diagonal. Right? So if I try to do a shear matrix to shear the bottom left away, right, then it gets 0, 0, which is bad. I can't solve it anymore. So you have to do the pivoting. Oops. Okay. Consider the following matrices. What is the resulting shape after applying AR to the circle? If you don't recognize it, R is a rotation by 45 degrees clockwise. Okay, last call. Okay, so the correct answer to a question you've seen before was A. Okay, it is multiply A times R, okay, times your shape, right, which means you apply R first and then A. Right? So if I rotate a circle, I get a circle, then I stretch it. Okay? Now, in the journals, a couple of people said they really struggled with these problems last week, so I brought them back. One of the things that they ask is, like, how do you build your intuition of this? Well, one is you build intuition by doing multiple examples. If I get a problem like this and I'm not really sure, I mean, I can reason about them, so it's straightforward, but how do you get that to begin with? My recommendation is take a couple of points. And I like to take points that are pretty easy to handle, like 1, 0, 0, 1, 1, 1. And multiply them through. And if I think of that the shape is this triangle, right? If I figure out what the triangle's doing, I have a pretty good idea what happened by this transformation, right? It started out as a nice simple triangle. If it gets flipped over, it can change, right? If you can't do it with 3, maybe add a 4th point so you can get something that's a little bit less symmetric, because sometimes it's hard to tell with symmetry. Okay? So consider the following matrices. Applying now R inverse. Yes, R is 45 degrees clockwise. Okay, last call. Okay, so who wants to defend the answer D? Brad?
So the first part of the range is just a circle. Then you do A, which increases the Y value by 2, or scales it by 2. Then it rotates it left from R inverse.
Okay, so it rotates it left. By left, you mean counterclockwise?
Clockwise.
Well, 45 degrees is clockwise.
Negative 45 degrees.
Negative 45 degrees is this way. So the answer is A. Last week I get this one wrong because when I typed it, I forgot to put the R inverse. I just had AR, right? So if I did AR, what would the answer be? E. It would just be stretched because we have rotated a circle, does nothing. So the correct answer was A. 1 or 2 more really quick questions. Fill in the blank. Vocabulary question. I thought I said 45 degrees was clockwise. So okay. So when somebody asked, I did say clockwise. I don't know, right? So this way. Right? I even turned to say it's this way, but right.
I think the trig 45-degree angle goes from the origin and rotates counterclockwise to 45 degrees.
Okay. So I will check the math on this one by actually multiplying points out and check, just to make sure. If the math works out that you're right, then I give everyone that said E the correct answer. Okay, we'll do one last one, and then I'll check that and let everyone know. So, Oops, it's already going. Dang, I messed that up. We're going to throw that one away. Start it over again. So fill in the blank. If the angle of incidence of the line is 90 degrees, it is a blank projection. Okay, and that will be it for today. See you next week. So I've updated the assignment to say next week are design docs. So in your design docs, I want to see the math worked out for here's how I decide whether or not a point is supposed to be on the line as you're doing it. That's one of the most important things is figuring out how you're doing that. I/O, don't really care as much about the I/O, right? And as a couple people have asked me, the example files I gave you have decimal points in them because 1.0 is a perfectly good number, so is 1 point, right? I don't have to have a 0, right? You should interpret them as numbers.
Question about the assignment.
Okay.
The files. The files that we read in.
Did you send me the number? Swan. 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 Did you send me this number?
In the files that you gave us, 2 files, you have 2 numbers on the top. One is the size, and the other one is
how many previous moves I have to look at to decide are you allowed to reuse those numbers. 0 means I don't look at all. 1 means if you just use cell, you use row 1, then I can't use row 1 or column 1. My answer.
no, I don't get it.
In the game, people are saying, I'm going to go here to here.
I know that I cannot start from this column or this.
So that you can't use this column, this row, this row, this column, and this column. If k equals 1, if k equals 0, then you can go anywhere you want.
That's the one I don't know.
K, right? K says how many histories do I have to look at. If k is 0, then you can go anywhere you want. You can go right here. If k is 1, I can't look at your last move. I can't use anything.
And if it's, for example,
2, then I can't use your last move or my last move. Right? Which in a 2x2 board means you can't move. But in a bigger board, there's big places to move. So it's a constraint on how many. So think of it as just literally, from a history point of view, you have the moves. How many of those do I look at to decide is your move valid? None. Your move's always valid in terms of history. 1, you look at the last guy and say, oh, you can't use that same 1. 2, go back 2. 3, go back 3.
what about, okay, so the first one is the size of the board, right?
Yes.
If you give us like a 2x2 and they insert like a number 3, is that something that...
That's invalid.
So
If
you
I
put
give
that
you
on
10 by 10
purpose?
and they do 12.
You did that on purpose on one of your files?
I don't know if I did it on purpose.
Because
I don't remember which files I uploaded.
so one of the files has like a size that is less than one of the... So...
4, 3, and there's 5s.
Exactly.
Yeah. Then, actually, that's probably a typo on my part. I'm sure that's a 5x3, 5x5 board. I will fix it.
Oh, okay.
That was not meant to be intentional. That was literally just making a mistake as I typed it. So I do have some more challenging ones for the other ones I was going to give you, but
Okay.
I'm not sure which ones I was going to have. So I'll
Thank
fix
you.
that. Thank you. Yes.
So I had a 0 on my first programming assignment.
Okay.
I didn't turn it on Canvas, but I did it on GitHub. So I was wondering if that might be the reason.
It might be. You should send mail to the TA so he can look at it. You are supposed to turn it on Canvas, but if
Yeah.
you turn it on GitHub, you can still get something for it.
Okay.
From our commentation, because I got a 0 for not having comments in it, but I was thinking of like comments in the program. What are we expected to like write them in a text document of some sort?
So comments that describe what you're doing and why could be in either place, right? For this next assignment, right, I'm not looking for the code yet. Whether or not you put the comments in the code, but I want you to design, so you're talking about for the next assignment? Right?
Yeah.
So I want a design that says, here's how the algorithm is going to work, right? Before you write the function to draw the line, I want you to think about here's how I'm going to draw the line. Here's the algorithm. Here's how I decide what points are on it, whatever. Right? It's a description of the math, right? Not just the code.
Good time for all of us.
Probably not before the next class does, but if we go out in the hallway, I'll have time. So, I just want to clean up before the next instructor comes in and says.
I'll hand this one back to you.
So
And I
did
sent you another email on Canvas with
And did
this.
you get it to work? Because the other student had the same problem.
I didn't get the phone to work, but I just kept using it the whole time.
Okay. Yeah, but we're going to have the same problem next week if you don't resolve how to get it.
Yes, I need to figure it out.
During my office hours today, between 11 and 1, I can turn this back on. And,
Yeah, I get out at 12:05 for my next class.
okay, so if you swing by,
What's your office number?
174.
In
Engineering. 3 doors down from 10.
Okay, cool.